Ok, bueno, buenas tardes nuevamente con todos. Les saluda Osvaldo Madrid. Gracias por unirse nuevamente a este nuevo webinar de la SPE Ecuador Section, análisis análogo comparativo para mejorar la recuperación de hidrocarburos. Nos acompaña como expositor en esta tarde el doctor Shaoqing Sun de la empresa C&C Reservoirs. Doctor Sun obtuvo su bachelor en Ingeniería de Petróleos en la Universidad de Northeastern Petroleum Institute en China en el año 1985 y su PhD en Ingeniería de Reservorios de la Universidad de Reading en el Reino Unido en 1990. Desde entonces ha pasado la mayor parte de su actividad profesional en la actividad de upstream en la industria petrolera. El doctor Sun tiene dentro de su background posiciones como consultor de geología para Chevron y como geocientista senior para Petroleum Information. Doctor Sun ha escrito y publicado más de 20 artículos científicos y ha de Advancing the World of Petroleum Sciences, Excellent Poster Award en el año 2007. El doctor Shaoqing Sun es cofundador de C&C Reservoirs en el año 1995 y actualmente ostenta la posición de jefe de ciencias. C&C Reservoirs ha tenido la misión de ayudar a las compañías de I&T a optimizar su desempeño mediante el conocimiento de los diferentes descubrimientos de hidrocarburos a nivel global. Esta visión ha sido compartida por muchas de las empresas majors y grandes independientes, tanto de Estados Unidos como Europa, quienes han provisto financiamiento e información importante sobre sus campos. Porque C&C Reservoirs está compuesto por geocientistas y ingenieros de desarrollos que han trabajado por más de 25 años en la investigación y centralización de la información de cientos de campos y reservorios alrededor del mundo. Esto ha llevado a C&C Reservoirs a ser proveedor líder en el sistema digital análogo de conocimiento, siglas en inglés. Más de 50 compañías y agencias de gobierno se han utilizado en este sistema para el proceso de toma de decisiones. La trama básicamente se basará en la explicación sobre los métodos de análisis, un rol importante para la evaluación de los potenciales y como base para la estimación de reservas, pero también para las fases de exploración y las fases de provocación de países donde la posibilidad de mediciones directas es limitada. La comparación del factor de recobro y el comportamiento de la producción de un reservorio con un reservorio análogo aplicable es clave en la optimización del desarrollo del campo y necesaria para entender las acciones requeridas para incrementar el rendimiento. Este estudio presenta un flujo de comparación de análogos basada en análisis sistemático de más de 1.600 reservorios. Con esto quiero dejar ya la palabra a Dr. Sun para que siga explicando y empecemos con su presentación. Dr. Sun, thank you so much for joining the Ecuador section today. I am sure that that's important, especially for Ecuador, where we are trying to optimize an increment of production in short and long term. Thank you so much, Dr. Sun. Welcome to the Ecuador section. SPE. Thank you.
Thank you. Good afternoon, everyone. Thank you for the opportunity to share our analog benchmarking workflow to maximize hydrocarbon recovery with the audience today. So for next 45 minutes, so I'm going to talk about why analogs. So what is the current issues, challenge with analogs? and what is our solution. So I'm going to focus on analog benchmarking workflow with the case studies. So this slide summarizes the key challenge our industry are facing. So we're having too much information while having very little wisdom. So today we're competing with our ability to put together the right information at the right time and think critically about it and make important choice wisely. So that's the quote from a very famous American biologist, Edward Wilson. So this quote really summarizes what we're facing our industry. So why analogs? So analog has been widely used in industry. The concept of analog is not new, but the methodology differ from one company to the next one. So many companies use analog in very informal, inefficient way. So analog provide the opportunity to learn from local and global experience, generate more insightful and creative ideas, from which better decision can be made in the following scenarios. So provide input when data not yet available for new assets, such as prospect or newly discovered fields, when direct measurement is very limited. Analog can be used to calibrate uncertainty range, validate ideas, concept, and assumptions, to finally help identify issues and opportunities to maximize asset value. So in short, analog intelligence combined with your own data and technology results in superior decision-making driving value. So analog methods is now form an integral part of resource quantification workflow. So this is a quote from the SPE WPC APG SEG latest petroleum resource management system book, so 2018 publication. So analog are widely used in the estimation of resources, particularly during exploration and appraisal phases, when information from direct measurement is limited. Analogs are frequently used in assessment of economic producibility, production decline characteristics, drainage area, and recovery factor. And also there's a consensus comparison with several analogs rather than a single analog is necessary to understand the full range of uncertainty. So let me share with you the common pitfalls and mistakes of analog application. So most of inappropriate application of analog analysis result from a lack of structured, standardized, and classified analog knowledge framework. So local analogs are necessary, but unable to help generate new ideas or capture the full uncertainty range. So that's the most common mistakes, common pitfalls. So people only use and rely on local analogs. The second point is when global analogs are in conflict with local data, users only select those analogs that confirm their pre-existing belief. So we call it confirmation bias. Analogs are chosen arbitrarily, relying on project teams' recommendation and knowledge from their own experience. So that's another common pitfalls. So people only use analogs at the last minutes, ad hoc basis. So finally, analog quite often are chosen too specifically for lookalike fields without considering what's the purpose of using analogs. So here's our definition of analogs. Analogs are defined as comparable fields or reservoirs relevant to a specific question or set of questions. Just like a doctor looking for analog for a certain disease. So really doctor will focus on the symptoms rather than look like of the human beings. Secondly, finding relevant analog for any specific questions is a process of empirical research. Problems of differing nature and for different objectives require a different set of analogs. Third point, users should focus on their specific questions instead of look-alike or geographically close analogs. The fourth point, the best practice starts with a broad set of parameters to find a wide range of analogs, then narrow the selection as appropriate to focus on the specific critical issues. So finally, it's critical to strike an appropriate balance between the number and the relevance of analogs. So here's our analog search selection best practices we have developed in relation with the client. So really analog selection depends on what you do. So we break down analog selection into four blocks. The first one is exploration geoscience. So you look for analog to validate play concept or calibrate prospect uncertainty range. So you focus on tectonic setting of analogs, could be tectonic setting for reservoir, source, seal, trap, deposition environment or lithology, trap configuration, and the geological age. So that's what you use to define play element. So once the discovery is made, you focus on the container, which is the job of development geoscience. So they look for analog to understand reservoir heterogeneity and connectivity. So they look for analog with similar deposition environment of sandy body type, diagenetic reservoir type, similar reservoir compartmentalization, both vertical and lateral, and then use network ratio. For reservoir engineer work for both exploration and development, they look for analog to understand the reservoir of wells producibility, recovery, development options. So they focus on hydrocarbon type, onshore, offshore, deposition environment or lithology, similar drive mechanisms, similar rock fluid properties, and then similar field size. For production management, so they're not looking for analog per se. So they're looking for best practices and lesson learned to maximize hydrocarbon recovery. So they look for analog with similar hydrocarbon type, development challenge, onshore, offshore, similar deposition environment or lithology, similar rock and fluid properties. Since at this stage it's mature asset, so they have all the subsurface geological and reservoir engineering production data. You just simply do the analog benchmarking against relevant analogs to identify critical issues and upside recovery potential. So just like we humans go to hospital doing the blood test to identify some issues, either cholesterol, sugar level, heartbeat, and so on. Isolate specific critical issues and focus on smaller number of applicable analogs to identify both best practices and lesson learned. So why analog benchmarking? Analog benchmarking is a key step in field development optimization and prerequisite in understanding the necessary actions required to maximize hydrocarbon recovery. The objective benchmarking is quantify potential expected ultimate recovery, understand the key controls on reservoir performance and recovery efficiency, identify best-in-class performers, and examine in detail what differentiates them, replicate best practices employed at top performing analogs. So finally, validate new opportunities for reserves growth. So what is our approach to analog benchmarking? So if you look at the challenge, the problems with the existing methodology, they mostly result from a lack of robust data model and absence of a holistic classification scheme. So you not compare apple with apple, but compare apple with orange without this robust data model and a holistic classification scheme. So what we've been doing in the last 30 years, the first is build a consistent reservoir knowledge base with standardized and classified geological and engineering parameters. Secondly, develop an empirical analog benchmarking workflow based on proprietary compilation of more than 1,600 global reservoirs. Thirdly, design for effective, practical, and repeatable application of analog analysis to all reservoir types, development scenarios, and production challenges. So we've tested the workflow against carbonate, classic, and fracture reservoirs globally. The workflow we have developed proved highly effective at quantifying resource potential, assessing production performance, and identifying best practices and lesson learned. Okay, so here's the 5-step workflow. So first step, define the problems to address and a critical question to be answered. So here's a summary of the most commonly sought after problems and objectives when it comes to analog benchmarking workflow. So the first question objective is, what's my expected ultimate recovery of my target reservoir based on analog recovery factor trend and understanding of key controls on recovery efficiency? The second question is, what's the upside recovery potential of my reservoir and what I can learn from the top performing analogs? The third question is, what's the production performance of analogs and impact water cut on production behavior? The fourth point, what's the current and likely future production performance of my reservoir from analog point of view? So the fifth point, to achieve that recovery, upside recovery potential, what's a well EOR, well reserve, well spacing, number of producer injectors, and annual plateau recovery or stoop required. The sixth point, so what is the mitigation measures to optimize my production and recovery? What is the EOR method screening and performance evaluation of analogs? Estimation of incremental recovery by infill drilling, secondary recovery, such as water flooding, gas injection, and EOR methods, including thermal, miscible, and chemical flooding. So finally, evaluate impact of effective reservoir management programs on production performance. So this is a summary of analog application for benchmarking purpose. Okay, the second step, parameterization of the target reservoir. So that's where you systematically catalog your prospect or producing asset using consistent standards and holistic classification scheme. So everything has to be structured, standardized in the same way for both analogs and also for target reservoir, so that you compare apple with apple. So the parameterization of target reservoir, including about 60 text and numerical parameters. The green color is the text parameters, and then black color is the numerical parameters. For field and reservoir level general, so we need to capture your target reservoir is onshore, offshore, hydrocarbon type, original reservoir pressure, temperature, pressure gradient, current production stage, and water cut, and the drive mechanisms. We need to capture well level information, such as well type, well pattern, completion, number of producers and injectors, well spacing, initial and plateau well rate, and well EOR. For trap, we need to capture and standardize trapping mechanisms, depth to top pay, productive area, and hydrocarbon column height. For rock, for reservoir and fluid properties, we need to capture reservoir age, deposition environment, lithology, diagenetic reservoir type, such as calcification, fracturing, wettability, matrix or bulk porosity, air permeability, reservoir thickness, and net pay, net growth ratio, API gravity, viscosity, mobility index, flowability, initial water saturation, gas specific gravity, and condensate gas ratio. For resources, we need to capture original in place, resource density, EOR, recovery to date of in place and EUR and recovery factor for both primary and ultimate. Improve recovery at the reservoir scale, including secondary recovery, such as water injection, gas injection, EUR methods, and conformance improvement techniques. Improve recovery at the well scale, including drilling, stimulation, artificial lift, sand control, well productivity optimization, well treatment, and workover. Finally, incremental recovery for infill drilling, secondary recovery for water injection, gas injection, and an EUR method. For production performance, dynamic data, we need to capture production injection rate, water cut, pressure, GOR, annual recovery of in place, and EUR, recovery to date of in place and EUR. Void this replacement ratio and injected for volume. The third step, quantification of resource potential. So that's where we establish recovery factor trend using key intrinsic parameters that have proven to have a major impact on recovery efficiency. So the third step, so resource quantification. So analog selection is based on a broad set of parameters to establish recovery factor, resource density, and a well EUR trend, and to understand key controls on recovery efficiency. So objective is to identify upside recovery potential, validate new opportunities for reserves growth, calibrate volumetric input and uncertainty, assess well deliverability. So here's analog search matrix for resource quantification for this column. Okay, so basically you use hydrocarbon type, whether it's oil, gas, condensate, whether it's onshore, offshore, lithology, carbonate, clastic, or basement, or deep position environment, shallow marine, deep marine, carbonate, build up, and so on, and diagenetic reservoir type, if you have one, like karst reservoir, fracture reservoir, what type of fracture we're talking about. And also the field size, in place reserve, and also recovery to date of EUR, which measure the analog's maturity in terms of production. Okay, so that's what you use for analog search. So further analysis, so we focus on 22 key controlling factors on recovery factor. Start with a natural drive on the left, to drive mechanisms, and the pressure depletion index. So pressure depletion index is defined as pressure drop per 1% of STOOP recovered prior to the introduction of pressure maintenance scheme. So for rock and fluid rock properties, we look at the matrix porosity, bulk porosity, air permeability, and wettability. For fluid properties, we focus on API gravity, viscosity, initial water saturation. For reservoir heterogeneity, we look at the net loss ratio, net pay, permeability contrast, defined as the highest permeability layer divided by lowest permeability layer. For trap, we look at depth to top pay, productive area, and hydrocarbon column height. For resource and recovery, we look at the in-place volumes, EUR, resource density, primary recovery factor, ultimate recovery factor, initial well rate, and a well EUR. So that's all you need, about 22 parameters you use for resource quantification. Okay, let's look at the case study. Case study 1 is a fractured microporous carbonate oil reservoir with very low permeability, 0.4 millidarcy. It's connected to a deep aquifer through the fault. You can see a really big challenge. What the initial drive is solution gas, aquifer, so early water breakthrough is big problems. And also the reservoir has been poorly fractured on the flank. It's a billion barrel field with book recovery factor 10%. So after 20 years production, recovery today has been less than 4% of STOOP with current water cut 67%. So what is the upside recovery potential? So what we can learn from analogs? So what we've done first is we established the recovery factor trend. So we focus on these 22 parameters, and we do different tests for different combination of parameters. So what we found is that the following formula worked best, give the best correlation. So air permeability divided by viscosity divided by initial water saturation times 100. Okay, you can see the correlation is pretty strong. The coefficient is 0.65. So here's your target reservoir based on this rock flow properties with the booked value 10%. Okay, so if you look at the recovery factor trend, if you follow the trend, that will give you 16%. So the 16% will be your reservoir technical limit. Okay, so how do we close the gap between 10 to 16%? So what we can learn from analogs? So this will be the step 5. I'm going to talk a bit later. Second case study is a high energy carbonate sand with good porosity, good permeability, normal API gravity. Initial development is vertical wells, solution gas cap drive. After 20 years of production, water injection started. So water injection has been focused on the high quality part of the reservoir, billion barrels filled with an expected ultimate recovery factor of 47%. So is a 47% reservoir technical limit? Are there any even upside potential for the 47%? Again, what we've done is we've followed the same step. We use these 22 parameters combination to see which combination parameter have the best impact for this reservoir type. Okay. So what we found is simple. So air permeability divided by viscosity give you the best correlation. Okay, 0.7. So here's your target reservoir. Okay, here's your value. Here's your booked recovery factor 47%. So you're right on trend with analog, global analog trend for carbonate and carbonate sand. Okay. So here's another way to look at the same reservoir from production dynamic point of view. So Y is water cut, X is recovery to date, which is recovery efficiency. You can see your target reservoir follow beautifully on the 45%, the empirical recovery factor trend. Okay, so this is empirical recovery factor trend for different period: low water cut, intermediate water cut, high water cut. So you can see 45%. So if you combine this two diagram, this chart with this chart, so that will give you the confidence from both static and dynamic data, give you both confirmation of 47% recovery under water flooding. So finally, this is a primary recovery index, a proxy for primary recovery factor. So we use machine learning application using 17 intrinsic parameters to build this algorithm for 4 different models, different reservoir models. The first model is offshore non-fractured classic oil reservoir. The second model is onshore non-fractured classic oil reservoir. The third model is conventional carbonate oil reservoir, primarily controlled by depositional phases, early diagenesis. And then finally, diagenetic oil reservoir, including karstic oil reservoir, fractured oil reservoir, carbonate classic basement. Okay, so here's what we use: pressure depletion index, pressure gradient, depth to top pay, structural compartment count. So how many structure blocks we have, trap flank deep, original oil column height, reservoir fluid unit, how many fluid unit, net pay, matrix porosity, bulk porosity, air permeability, viscosity, bubble point pressure, pour point temperature, original oil saturation, original water saturation, and resource density. So use different combination to create this algorithm for different models. Okay, so this is a very powerful tool to predict your recovery and natural drive conditions. Okay, so quite often the primary recovery factor is not always available. Now, with the 17 parameters, using machine learning application for each of the model, we can pretty accurately predict your recovery efficiency and the natural drive conditions. So step 4, analyze, normalize production and injection performance data from applicable analogs. So analog selection here is based on narrowly defined set of parameters relevant to the characterization and assessment of production performance. Okay, analyze production characteristics of analogs, evaluate impact of water cut on production behavior, determine well spacing, number of producers, and annual plateau recovery of stoop required to achieve the upside recovery potential. To validate production profile derived from classical reservoir engineering methods or simulation models. So analog selection on the right focus on, apart from the hydrocarbon type, onshore, offshore, lithology, environment, diagenetic reservoir type, field size, recovery to date. Also we add API gravity, error permeability, maybe even natural ratio. So now with all this about combination of these parameters, so that will give you really applicable relevant analog from production performance point of view. Here example is offshore fractures, microporous oil reservoir. As you can see from the top chart, so the higher recovery, so X is recovery to date, Y is water cut. So the higher recovery analog, the best performance, have a gentle slope. You can see the gentle slope. That means they're more efficient. Okay, more efficient recovery. For the lower recovery analog, which poor performance, which less than 15% recovery, you can see more unstable, very steep slope of the chart, of the curve. The lower graphic is the same data, it just show differently. So you just show normalized production annual recovery of stoop in place, and then X is recovery to date. So it's normalized production curve. You can see this is a higher recovery and this is lower recovery. You can see these two distinctive group. So now with our analog approach, we can look at the reason behind all this, the difference in performance. So here's the statistical analysis of this curve. Look at P10, P90 range of analogs. Okay, so what is the build-up duration? Build-up duration of analogs, plateau duration, and then plateau recovery percentage of stoop, plateau annual recovery percentage of EOR, and then horizontal well initial well rate. You can see the P10, P90 range, P50, and horizontal well EOR, vertical or deviated well spacing, horizontal well spacing, and horizontal well distance between producers. So here's a summary from the analogs. So the final step, we call them identification of best practices and lesson learned. So that's where you isolate specific critical issues and focus on smaller number of applicable analogs to identify both best practices and lesson learned. Okay, so yeah, the three objectives. First objective, identify mitigation measures to optimize production and recovery, such as well type, well pattern, completion, well placement, pressure drawdown, infill well, pressure maintenance, and conformance improvement techniques. Secondly, assess effectiveness of achieving incremental recovery by infill drilling, secondary recovery such as water injection, gas injection, EOR methods. So finally, evaluate impact of well-scale improved recovery methods on production performance, such as drilling, stimulation, artificial lift, sand control, well productivity optimization, treatment, and workover. So here again, you come back to the case study one. So fractured microporous carbonate oil reservoir. You can see the trend line, recovery factor. Here's your target reservoir, 10%. Here's the gap. The technical limit is 16%. Okay, so how to close this gap? So let's focus on specific challenging issues. So the specific challenging issue for the target reservoir is connected to a deep aquifer through central graben fault. So you have water cooling problems, water flooding problems, poorly fractured on structure flank, and a low, very low matrix permeability, 0.4 millidasty. So based on these specific critical issues, so we found three analogs, so three applicable analogs, Halfdan, Dan, and Waldemar. Okay, so these three analogs have their match to the target reservoir more closely as far as the critical issue are concerned. Now let's focus on these three analogs. See what we can learn to close this gap. Okay. The first one is Dan field. So Dan field is from Denmark. You can see very low permeability, really poorly fractured reservoirs. It's 2.8 billion barrels fields. So you can see the drilling of long horizontal wells, multi-zonal hydraulic fracturing, and high rate seawater injection have done magic to increase production dramatically. Okay, led to the plateau. Also, selective completion are used to isolate individual fractures and control the injection. So you can see a successful implementation of advanced drilling and completion techniques and effective water injection led to an estimated ultimate recovery factor 28%, which is much better than the target reservoir. So here's production curve, water cut. The blue is water cut, green is oil production. So the second one is Halfdan. So Halfdan is very similar to Dan, but it's much younger field. So this discovered and developed much later, 20 years later. So Halfdan already learned from the Dan fields. So already built the best practice. Okay. So again, it's pretty big fields, 1.6 billion barrels fields. As you can see, it's a long horizontal wells for both producer injectors. Fractures are induced by multiple asset fracturing in producers and high rate water injection injectors. Selective completion provides control on individual production injection zone. So successful implementation of high rate water injection, drilling of long horizontal wells, and asset stimulation led to an estimated recovery factor 38%. This is production profile. Finally, let's look at another analog, lower outcome. So Waldemar. So 725 million barrels oil, very low matrix permeability, very similar. So it's really heavily faulted with a number of isolated compartments connected to deep aquifer. As you can see, basically it's under aquifer solution gas dry. So water was produced from the start up. So water cooling is big problems. So because of lower permeability, well has to be hydraulically fractured. So poor control of production and a lack of effective secondary recovery program led to an estimated recovery factor of only 14%. So this is very similar to the target reservoir. So recent numerical modeling indicate an incremental recovery 11.5% by lean gas injection. If you combine these two, that give you 25%. So that would be the technical limit. So gas injection could do the magic. So here's the production history curve. You can see oil production drop because the water cut goes up dramatically. So now if they do, so today water cut is 48%. So if you're doing lean gas injection, that could revitalize the production history. So let's summarize what we can learn from analog, from reservoir management practice point of view. Okay, let's look at the well type. Horizontal well, vertical or divided well, multilateral extended reach well. Well pattern, you can see line horizontal injection production, and then radial horizontal irregular, and then completion, and then perforation. So secondary recovery methods, most common one is water injection followed by gas injection, conformance improvement, selective injection, water plugging, modify injection pattern, and drilling. So most common is side tracking, infill drilling, step-out drilling, stimulation including matrix acidization, acid fracturing, and hydraulic fracturing, and artificial lift, gas lift, ESP, and including also well treatment and workover. So if you do water injection, what is their incremental recovery? So we use machine learning to establish the baseline. Baseline is primary recovery factor equal ultimate recovery factor. So there's three fields like Cracker, Valdemar, and Terra. So there's only these fields have been producing at the primary recovery only. There's no water flooding. And other analog have been through water flooding, but the result is different. Okay, highly variable. The highest one gives incremental recovery aquaphase 28% by water injection, and then another one 24%, and then there Warhol 9%, and then 21%. So here's the one to give you a pretty variable incremental recovery, and then we need to understand why the water flooding the result is different. So now is another case study show the test viability of EUR method for onshore classic heavy oil reservoir. So this heavy oil reservoir is onshore. The depth of reservoir, the viscosity is about 100 CP under reservoir conditions. The depth is about 4,700 feet. Okay, so we use global analog to establish recovery factor trend, but to establish the viscosity and depth trend by EUR method. You can see here the EUR method, the limit, depth limit is about 3,700 feet. So beyond this depth, EUR method is not going to work because it's too deep. Okay, so here's the target reservoir. You benchmark it. So we'll show you your target reservoir is not suitable for thermal recovery. Okay, it's very clear through this chart. So your reservoir is too deep for the thermal recovery. So, but for chemical flooding is okay. You can see the many chemical flooding examples. So you can do chemical flooding for target reservoir. Now let's say if we do water flooding for the onshore classic heavy oil reservoir, what would be my recovery? Okay. So here's the recovery factor trend. So X is ultimate recovery factor, Y is the mobility index, defined as air permeability divided by viscosity. Okay. So the target reservoir mobility index is less than 10. Okay, it's around 5, between 1 to 5. So if your mobility index between 1 to 5, 1 to 10, around 5, so that will give you the range of recovery factor by water flooding. Okay, will be minimum will be 11%, maximum will be 24%. So here will be your right analog for the mobility index based on the recovery factor trend. So that's the end of my presentation today. So please feel free to ask any questions.
Okay, thank you so much, Dr. Sun, for your excellent presentation. You have reached important technologies, important things that are now in Ecuador or the common conversations. Okay, a todos los que nos se han unido a este webinar, si tienen alguna pregunta, por favor hacerla a través del chat de Teams que tienen a la mano. Tengo un par de preguntas aquí. Dr. Sun, I have a couple of questions for you. Es importante mencionar que Dr. Sun nos está acompañando desde la ciudad de Beijing, en China. Está ya todavía madrugando, así que le agradecemos a Dr. Sun también por reunirse con nosotros desde ese lejano lugar. Dr. Sun, the first question for you. In the slide of primary recovery index, a proxy for PRI, how the ML application justifies a perfect correlation for 3 different sedimentological reservoir nature. non-fracture, clastic, conventional carbonate. I assume fracture reservoir and diagenetic reservoir. That is the question, Dr. Sun.
Yeah, so to build this recurrent factor trend, so first you have to build the model. So the model has to be unique. So really, you can't build one algorithm for mixed reservoirs. Really, we start with a high level 4 categories. So one is we separate onshore and offshore. So really onshore classics, but it's non-diagenetic. Okay, so really no fracture, no calcification. So onshore classic oil reservoir and offshore classic reservoir. So these are 2 models, different models, because onshore, offshore is a different challenge. And third model is a carbonate. So carbonate is very different from classics. So again, for carbonate, we have 2 models. One is a conventional carbonate, which is mostly carbonate controlled by environment, by diagenesis, with only early diagenesis, such as build-ups, carbon sand, and then dolomite, early dolomite, and then the diagenetic. The diagenetic is the final category. So diagenetic means fracture reservoir, karst reservoir, hydrothermal reservoir. It really means the reservoir is unrelated to depositional phases and stratigraphy. So completely controlled by fracturing and calcification. For this reservoir is very, very unique. So therefore, for different models, you use different parameters. But altogether 17 parameters, that's all you have. So for different model, you use different parameters to build the algorithm, the correlation. Okay, thank you, Dr. Sun. I have another question here. Can DAX predict any problem about pipelines and pumps, or is just limited to solve production problems? Yeah, so our technology is focused on subsurface technical aspect, subsurface. So really, the key objective is the resource quantification. Okay, so to quantify resource, you have to look at the static data and then dynamic data. So we look at both static and dynamic data point of view to quantify resource. So obviously, apart from raw fluid properties, apart from reservoir hydrogeneity, apart from the natural drive strength, and also you need to look at the development concept. You need to look at the reservoir management programs. You need to look at improved recovery at well scale, like well type, wells pattern, well spacing, and also kind of stimulation, artificial lift, and then sand control, workover. Really, so that's any aspect which impact the recovery, impact the production performance. So that's where we focus. Okay. Anything above ground, that's not our business. Okay, focus on production. Sí, de acuerdo a la presentación que nos ha hecho Dr. Sun, efectivamente, bueno, lo que hemos visto es una serie de bondades que puede tener este análisis en cuanto al análisis del factor de recuperación, el índice de recuperación y la optimización de la producción, el incremento de la producción, que son todos temas, como ustedes conocen ahora, del día a día en nuestro país, ¿no? Cómo podemos ir en la implementación adecuada de proyectos de recuperación secundaria o EOR, etcétera. Dr. Sun, I have another question for you. Could you please comment if you foresee this sort of empirical analog analysis being done by ways of artificial intelligence? Where would they leave our input and relevance as a petroleum engineers? I'm not sure if I really understand the question 100%. So could you rephrase the question? Is this a method, this analysis that you are proposing to us related to artificial intelligence? You mentioned in some part of your presentation that this you mentioned machine learning. So what is the background of this analysis?
in terms of the software or something like that?
Okay, perfect question. Yeah, and also that related to the first question, the primary recovery index. So basically, the question is, so you don't build one algorithm for different reservoirs. So really, that's very, very important. You need to classify the reservoirs. So once you classify reservoirs, because as human, very, very difficult for our brain to understand so many parameters and how they control the recovery. 17 parameters, too many for our brain to work. So we use machine learning. So we train the computer using a well-established algorithm. So we use a well-established algorithm and train the machine and to use normalized data. So every data is standardized, is normalized, and we give a score. Okay. So the machine can give the score using the score and try to correlate each parameter and then give each correlation a score. And then the machine will add up the score. A machine will try a different combination. So machine can run hundreds of thousands times, run different correlation, different combination very quickly. So machine will produce the best fit. Really, so really, we can't. If we do it, we'll take out 5 years to do all this correlation. But the machine can do it 5 minutes, try hundreds of thousands times. Okay, because if you look at 17 parameters. The combination of 17 parameters is we're talking millions of possibilities, but machine can do it very fast. Okay, different combination, different correlation with the recovery efficiency. So that's how we do it. So effectively, it is artificial intelligence using machine learning based on the well-established algorithm. Okay, and then we just pick one. We just pick one. I think there are probably 10 available algorithms. So we just pick the best one for our purpose. So our purpose is very, very specific. We try to establish recovery factor for primary recovery and natural drive conditions. So how the rock fluid properties, how the reservoir hydrogeneity, how the drive impact my primary recovery factor. So very, very specific objective using machine learning. Really, for machine learning to work, you have to be very clear what problem you're trying to resolve. Number two, the data is garbage in and garbage out. You have to make sure you have quality, consistent data. They're all standardized, all classified, all reliable. So then for the machine to work, you have to have all this. And then you have to understand, you have to build a model, different models. This is really powerful tool. So if you don't have a primary recovery factor data, we can use machine learning to help predict, forecast your recovery. It's probably 85% accuracy, more than 80% accuracy. Very, we have tested so many times. It is more than 80%, 85%, 90% accuracy.
Okay, thank you, Dr. Sun. Para resumir la última parte de la respuesta, el método pues podría predecir el factor de recuperación con entre un 80 y 85% de certeza, ¿no? I have a final question for you, Dr. Sun. I don't know if you are familiar with the reservoirs that we have in Ecuador, but in some cases we have some seasonal strong aquifers that affect the behavior of the reservoir. How would you propose solving such problems in a field development plan? What else could be done to increase the recovery factor when you have an aquifer, a seasonal aquifer that are working on the reservoirs affecting its behavior?
Yeah, but it's very, very good question. So I think in DAX, so it's everything are standardized, classified. So we do have analogs with similar aquifer strength. So we classify aquifer by pressure depletion index, by strong aquifer, moderate aquifer, and weak aquifer. Okay, so I think the challenge for strong aquifer is not just challenge for aquifer to work. So sometimes can work for you, and sometimes work against you. So all depends on how you control it. If you control it well, strong aquifer give the highest recovery. If you control it well, okay, and also depends on what reservoir. For example, if you have a fault, if you have a fracture, connect to the aquifer, and if you drill the well placement, the completion is very, very important, and also the output, the production rate, also the change the choke size, the perforation, the well placement, the pressure drawdown, and so on, and also the conformance improvement technique. So we have many examples globally. So how do we use conformance improvement technique, like a zonal injection, water flooding, modifying injection, and so there's many different ways to really control the water, okay, using different intelligent completion, selective completion. So really from completion, the conformance improvement technique, there are many ways to do it, and also well placement, also the drawdown. It also depends on what kind of reservoir we're talking about. Depends on, do you have a fault, connect aquifer? Is it a regional aquifer, deep aquifer, or it's perch aquifer? And what's the size of aquifer? What's your reservoir? And also what's your development strategy? So I think we have many analogs globally for different challenge you can learn for your specific situation. So I don't think that's a uniform formula you can say yes or no, because every reservoir is different. For example, if you're talking about very simple reservoir offshore turbidite, if you look at offshore turbidite, okay, strong aquifer gives the highest recovery. Sometimes, quite often, you don't need water injection, gas injection. So the primary recovery, if a strong aquifer, if you manage it properly, give you the highest recovery.
Thank you, Dr. Sun. Well, the very final question is most of the fields in production here in Ecuador are mature fields that have been in production in some cases for 20, 25 years or more. Do you see an opportunity for this analog analysis benchmarking in the oil fields in Ecuador based on these conditions that we have to increase the recovery factor, to increase the production, which is what we are looking now very hard?
Yeah, it's a very excellent question. Actually, that has been the case for most of our clients, and actually the case for our benchmarking workflow is designed for. It's really it works best for mature assets, because for mature asset you have everything. You have the subsurface technical data, you have production data, water cut data. So what we do is, so we can benchmark your production performance based on your rock flow properties, the reservoir heterogeneity, drive, and then your water cut performance. So once we benchmark it, find the right analogs, you can see the gap. You can see how their similar reservoirs other operators have done. So what you can learn from their best performance. So quite often has been the case. If you're the operator for your reservoir for 20, 30 years, you think you know everything because you've been doing this for your entire life. But actually there are quite often the simple techniques, simple improved recovery techniques have not been tried in your reservoir, but has been tried elsewhere. The technique alone is not new, but it's new for you. So you don't have to always look for new technology. Sometimes existing technology has proved working elsewhere. You just need to learn from other operators how this existing technology can work for your reservoir. I think it's the same for exploration. You need to open your mind. You need to really get out of box thinking and think about the unlikely. So so basically what we can do is try to establish the reservoir technical limit. So really for your reservoir, for your challenge. So what is the theoretical limit? So how you can close the gap? So let's say the limit is 40%. You have achieved 35%. So how you can close the gap? Close to 5%. If you have 1 billion barrels filled, 5% is a lot of oil.
Thank you. Very, very interesting answer, Dr. Sun. Bueno, la respuesta de Dr. Sun, como para resumir, y acá que siempre estamos tratando de intentar nuevas cosas en Ecuador, pero tenemos siempre ese recelo de que son nuevas para nosotros. Pero Dr. Sun nos dice, bueno, tal vez es nueva en su campo, en su país, pero ya ha sido probada en otros lugares. Y esta metodología nos permitiría mediante el benchmarking, mediante la comparación de las características de los reservorios, del reservorio con sus respectivos análogos en otras partes del mundo, ver si las nuevas técnicas que se están proponiendo realmente van a dar los resultados esperados bajo el conocimiento de que ya han sido probadas en otros lugares en reservorios análogos muy comparables. No quiero dejar pasar la última pregunta, aunque creo que es bastante clara la respuesta. Dice, ¿sería posible tener un software en el cual se ingrese las características de un reservorio y se obtenga el factor de recobro primario o secundario esperado? Dr. Sun, please, just one additional question for you. It is possible to have a software in which we can enter the reservoir characteristics and obtain the recovery factor, the primary recovery factor and the secondary recovery factor expected? I think the answer is very clear, but please.
Yeah, so your question is how we can break down the primary, secondary, and the tertiary recovery factor, right? So the DAX, we have different parameters. So for example, our machine learning will help you establish a primary recovery factor, okay? And also we have a parameter called incremental recovery by water flooding. So now DAX have the capability allow the analysis of incremental recovery by water flooding and gas injection. So we have a water flooding or gas injection incremental recovery for analogs. And also we have another parameter, we call them incremental recovery for EOR. So also for all the C&C analogs, we'll tell you if you do miscible gas injection, what's incremental recovery, if you do thermal, or if you do chemical flooding. So we do break down the recovery factor by category, primary, secondary, and EOR.
Okay, but for that there is some kind of software tool that you use to do this analysis, right? Using the benchmarking and doing some kind of iteration, benchmarking with other reservoirs around the world.
Yeah, so basically for the analogs, what we have done, we use a different methodology to get the numbers. The first thing is, for example, when we do the analysis, doing the research, so we look at use machine learning, and then also with the check everything, we get primary recovery factor. And also for water flooding, we use decline curve analysis. So we use decline curve analysis to look at the incremental recovery for water flooding and for EOR. So basic C&C, we use a very conventional approach to decline curve analysis to get incremental recovery for water flooding and then for EOR flooding. For primary, we use machine learning to get it. But from analog point of view, basically that we have all the numbers. So when we come to benchmark your reservoir, again, we use very similar approach.
Okay, thank you so much, Dr. Sun. Bueno, machine learning es básicamente la herramienta aquí que permite hacer todo este tipo de análisis tan interesantes. Tenemos una herramienta poderosa. Creo que ahora en el país estamos necesitando de cualquier cosa que pueda ayudarnos justamente a eso, a incrementar la producción, a mejorar el factor de recobro, a orientar de mejor manera las decisiones respecto a proyectos de recuperación secundaria o terciaria. Y creo que es una herramienta que, como vimos, hace un análisis bastante integral de todas las opciones que podrían presentarse para mejorar las condiciones y el comportamiento de los reservorios de manera de tener la mayor producción posible.
I have a final comment. I have one comment.
Okay, Dr. Sun.
Yeah, my final comment. I think for recovery factor prediction, I think we need to get the baseline right. The baseline is the primary recovery, so we must get primary recovery right. And then in terms of secondary recovery, water flooding, we have another tool, C&C, we have developed. We call Empirical Chart. The Empirical Chart, that's based on many case studies, onshore, offshore case studies. So we have established water cut versus recovery to date. That's Empirical Chart. So that's also validated by relative permeability. So that empirical chart also is another tool to benchmark, to give you some really good idea about the water flooding incremental recovery. So if you have water cut data and recovery efficiency, we just plot on the C&C tool, the empirical recovery chart. So that will give you another way to look at the water flooding incremental recovery.
Okay, thank you. Dr. Sun, nos comentaba sobre cómo podemos trabajar para incrementar el factor de recobro con inyección de agua, no water flooding. Well, thank you so much once again, Dr. Sun, for joining the SPE Ecuador Section today. It's been very good presentation, excellent presentation, and very useful for us at this moment here in Ecuador. Agradezco nuevamente a todos los asistentes. Creo que ha sido una charla bastante buena y fructífera. Ojalá pueda ser de interés de todos a ir introduciéndose en estos temas que creo que podrían ayudar a la industria ahora en estos momentos que tanto lo necesita. Nuevamente, gracias a todos. Dr. Sun, thank you very much. I have a comment here from one of the attendees. Thank you very much for the presentation. We have to learn from the experience of others and apply them if they fit our reservoirs. And that is a good comment, I guess. It's been a very good presentation and very useful, Dr. Sun. Thank you so much. Have a nice day in China y tengan una feliz tarde todos acá en Ecuador. Nos veremos la próxima semana en un nuevo webinar que lo tenemos programado ya. Gracias y buenas tardes a todos.
Thank you for the opportunity. I really enjoyed it. So I will share a copy of my slides with you. So I will send you a copy. You can share with the audience.
Okay, thank you, Dr. Sun. When Dr. Sun is telling us, el doctor Sun nos está diciendo que va a compartir su presentación y se la pondrá, como siempre, en la página web de la SPE para que todos la puedan observar. Thank you, Dr. Sun. So your presentation will be shared through the SPE Ecuador Section web page, as we normally do it.
Okay, I will send it to you. I will send it to my colleague, Ricardo.
Yes.
So Ricardo can pass it to you.
Yes.
So
sure.
have a great weekend. Thank you so much for the opportunity. Bye-bye.
Gracias.
Everyone.
Gracias a todos nuevamente. Una buena tarde. Gracias.
Yeah. Bye-bye. Bye.
Bye.